Everyone. So the topic is scaling characteristics of hydrodynamic turbulence, and the goals of my talk are twofold. I will show you that if you consider regions and say homogeneous isotropic turbulence, here I'm showing you regions for a visualization of vorticity component that is normal to the plane shown here, and I'm showing you these. You can see these structures that are visible, but these are characteristically absent in isotropic turbulence. But when you filter the field, when you focus on regions which have high circulation, here gamma is the circulation, I will explain this in a minute, and when you focus on high circulation magnitude regions, you see that vorticity has structure, and the structure in turn is related to scaling. So I'm going to show you that if you focus on circulation instead of say velocity differences, as one typically assumes to scale a certain way, you can see a very easier or more trivial scaling than the velocity differences. My talk is also going to serve as a nice segue to the next talk by Sasha. So I'm going to show some numerical data based on some of his theories. So the basic goal is, can we have true scaling in turbulence? Turbulence, as you might already know, is characterized by high gradient vortical regions. Here vorticity is the curl of the velocity, and here I'm showing you a snapshot of the entropy field. You see that these entropy structures are tubular in nature. They're also non-homogeneous. You can see clusters of these worm-like structures in one part of this plane, and you can see emptiness in the center of this visualization. So this is very non-homogeneous, and if you take a line trace of the entropy, for instance, and say divide it by its mean, you will see something like this. And the mean of the entropy is very close to 0, but you will see fluctuations which are close to 1,000 times the mean. So this is the problem in turbulence. This is also called intermittency. And typically what one does to quantify this intermittency is one considers velocity increment moments. So here delta RU is a velocity difference across a fixed scale r, and you typically take moments of this velocity differences, and if you take, for instance, the pth moment of the velocity difference magnitude, and in a certain range, let's call it the inertial range, this will scale as r times r power zeta p, and what we actually find is zeta p is a non-trivial function of the moment order. So in particular, zeta p is not linearly related to p, so the Kolmogorov scaling is p thirds, and what we find is zeta p has a more complex behavior on the moment order. So this leads us to the phenomenon of multi-scaling. So each moment order for the velocity increments has to be dealt with in its own way. So you can't get, for instance, in a Gaussian field, you know the first two moments, you can build the other moments, and you can't do that for a turbulent field. So multi-scaling can also be thought of as no scaling, depending on your philosophical bent of mind. So what I would like to do is, instead of considering velocity increment moments, I would like to at least quantify the scaling in the average vorticity field. And this average vorticity field, as I've already shown you, are high vortical regions. So I'm going to first define average vorticity. Average vorticity is directly proportional to the velocity circulation. The velocity circulation here, represented by gamma, if you consider a loop, here I'm denoting it as C, and the area of this loop is A, and this is a simple loop which is fixed in space, and it's a closed loop. And if you take the line integral of the velocity, you can define the circulation. Using Stokes' theorem, you can also use the vorticity flux, which is normal to this area, to define the circulation around this loop C. So once you do this, you can define the average vorticity. Here I'm denoting it with these angle brackets. This is for average. This is simply the circulation along this loop C divided by the area. This is the average vorticity. So if we can say something about high gamma regions, so high circulation regions, then we can quantify this local average vorticity. So that's the goal for my talk. And hopefully these high circulation regions are independent of the shape of the contour C, because this is an parameter here. So if circulation were to depend on the shape of the loop, then you can't really have a scaling theory for circulation, for instance. So I will be using data from direct numerical simulations of three-dimensional turbulence. So what I'll be doing is I'll be considering a fluid with a constant density in a periodic box. And the box has a fixed length, say L. And this box is being shaken with some energy, so I'm forcing the velocity field. Or you can think of it as stirring the velocity. And I'm stirring the velocity only on the large scales of the order of the box size. The Reynolds number of this fluid can be defined as an inverse of the viscosity. I'm also going to use a Taylor scale Reynolds number, which is roughly the square root of the Reynolds number. When you look at the line trace of this velocity field, normalized by its standard deviation along, say, one edge of this cube, what you see is something like this. At a low Reynolds number, you see, for instance, a signal like this. But as you increase the Reynolds number, in this, we are increasing the Reynolds number by decreasing the kinematic viscosity. You see that the signal has more small scale, fine scale features in it. And this is because the nonlinearity is, in the Navier-Stokes equations, is spreading the energy to the small scales. The smallest scales in the flow are given by the Kolmogorov scale, and the Kolmogorov scale roughly the ratio of the Kolmogorov scale to the box length roughly goes as a power of the Reynolds number. So larger the Reynolds number, the box size is fixed, the Kolmogorov scale becomes smaller. So for very large Reynolds number, there exists an inertial range. This inertial range is that range which is far smaller than this box size, and it's far larger than the Kolmogorov scale, and this is our region of interest. So before moving on, I would like to quantify what I mean by the inertial range. In order to quantify this inertial range, we have this exact asymptotic equation from the three-dimensional Navier-Stokes equations, which I have written down here. So if you consider the velocity increments, which are separated by a distance r, and I take the projections of these velocity differences along the separation, these are called the longitudinal velocity increments, and I take its third moment and I divide it by the scale size r, and I take this limit, first limit Reynolds number going to infinity, and then the limit as the scale goes to 0, then this should asymptotically yield the right hand side of this equation. This is proportional to the average dissipation. So what I'm showing you in this plot is precisely this numerical verification for this 4/5 law. What I'm doing is I'm plotting the left hand side and I'm dividing it by the right hand side. So if this equation is asymptotically valid, then with increasing Reynolds number and decreasing scale, I should see a plateau at unity. So this is the numerical verification for this. And what you see is precisely this. As you increase your Reynolds number and you decrease your scale size r, you see that this plateau is moving in the direction of this arrow towards unity, and this is my inertial range. So what I'll be doing is I'll be focusing on this inertial range, and when I'll be considering circulation, I'll be considering circulation for loops with both dimensions within this inertial range. So if I'm calculating circulation, I'm going to be taking loops and I'm going to be moving them around the field, but both the dimensions lie within this range. The first question I would like to address are these large circulation amplitudes which we are interested in sensitive to the contour geometry or not? So to do this, what I'm going to do is I'm going to take two different contours with the same area but different aspect ratios, and I'm going to see how these statistics of the circulation depend on the loop aspect ratio. So I'm going to consider Cartesian loops, and I'm going to consider planar loops first. So we have something called the area rule for velocity circulation, and what the area rule says is if you have the contour edge in the inertial range, then the distribution of circulation scales with the minimal area, and this was given by Migdal back in 1994. So if you consider a contour C, and you can have infinite areas enclosing this contour. So I'm showing you two such areas. One is the planar area, which is also the minimal area. I'm also showing you a non-minimal area, which is twice the minimal area. So what the area rule says is that the probability density function of the circulation is a unique function of this minimal area. So in a later work, Migdal also showed that this area rule holds as an exact result for planar loops in 2 and 3 dimensions. So first I'm going to show you a numerical verification of the area rule before proceeding towards the average water stay. What I'm showing you here is the probability density function of the circulation considered for this contour C, and I'm considering a fixed area which is shown here with edge lengths L1 and L2, and what I'm going to do is I'm going to vary L1 and L2 such that the product is the same. So the area is the same, but the aspect ratios can differ, and both L1 and L2 lie within the inertial range which I've already showed you. And if I calculate its PDF, and I'm showing you as a function of the circulation normalized by its, say, standard deviation times L, and what you see is all these 3 different contours here, their PDFs collapse, at least till, except the tails, they collapse really well. And you can fit this PDF using a pure exponential, but the pure exponential is modulated by the square root of the circulation, and this square root of the circulation also comes from Migdal's 2019 theory. So circulation statistics sensibly is independent of the loop aspect ratio as long as both the sides lie within the inertial range. This is the conclusion from this plot. Now from this PDF I can calculate moments, and I'm going to see how the moments of different orders obey the area rule. So I'm going to see whether this ratio of these moments depend on the loop aspect ratio or not. So what I'm going to do is, as before, I'm going to consider a fixed area A, and I'm going to vary the edge lengths. So I'm going to take very thin rectangles shown here, and I'm going to progressively go towards the square loop which has an aspect ratio of unity. So the thin contours here, their loop aspect ratio is very small, and I'm showing you this ratio of these moments which are normalized by their powers, and I'm showing you its logarithm as a function of the loop aspect ratio. So what you see is these filled symbols are symbols that correspond to the inertial range, and these unfilled symbols correspond to contours where at least one edge is outside the inertial range. So if you take the 4th order moment, for instance, you see that there's a dependence of this ratio of these moments on the loop aspect ratio, and you see that as the aspect ratio drops below, say, half, you see that these ratios depend on the aspect ratio. But what happens is, as you increase the moment order, so from top to down, you're increasing the order of the moment from 4 to 12, this ratio of this moments, or the logarithm of the ratio of these normalized moments, are decreasingly sensitive to the loop aspect ratio. So the conclusion here is that these circulation moments increasingly become independent of the aspect ratio of the planar loops. So these high circulation regions are less sensitive to the specifics of the loop geometry as long as the edge lengths of the loop lie within the inertial range. Now I've considered planar loops, but what about non-planar loops? It's a 3-dimensional field. You can also have more complex loops. For instance, you can have a loop like this. This is a soccer gate, and I'm showing you the dimensions here, and I'm going to call this loop C1, and I'm also plotting its minimal surface. The area rule proposed by Migdal says that the PDF of the circulation is a unique function of the minimal area. So in order to test this, what we did is we took another planar loop whose area is the same as the minimal area of the loop C1. So this is a different loop C2, but it has the area which is equivalent to the minimal area of C1, and you can calculate its PDFs as before. And what you see here is that if you plot the PDFs of the circulation for both these loops, you see that they actually differ. In fact, if you see that even when you get outside the core of the PDF, you see that the data differ. So the conclusion here is that this area rule doesn't apply for these unnormalized circulation PDFs. But what happens when you standardize the circulation with its moment? For instance, here I'm normalizing the circulation by its standard deviation, and you see that the collapse is much better. So you see that at least up to 8 standard deviations, that the PDFs of these 2 different loops, C1 and C2, which have the same minimal area, collapse very well. Outside these 8 standard deviations, you see that there are differences which can be statistical. So the conclusion here is that the area rule is more accurate for normalized circulation moments. Normalized moments, for instance, you consider the flatness or the hyperskewness, for instance, than for the raw moments themselves. So the basic conclusion from what I've shown you is that the area rule model works well for planar loops, and especially with increasing moment order, the PDF tails converge for loops with a fixed area but different aspect ratio inside the inertial range. The normalized circulation moments appear to agree with the area rule model better rather than the raw moments themselves, and that's why I'm going to consider circulation flatness, for instance, and check. And then once I consider a normalized moment, I can forget about the loop geometry, because as long as it's in the inertial range, then it doesn't depend, the statistics don't depend on the specifics of the loop. So I'm doing this now. I'm showing you the circulation flatness. So I'm considering a square loop now. So because I'm considering flatness, flatness is a fourth order moment divided by the square of the second order moment. So I'm going to consider a square loop, and I'm going to parameterize this loop with its edge length, say r. And I'm going to plot this flatness for different loops with different areas or different edge lengths r. And I'm doing this for different Reynolds numbers. And what you see is, for the lowest Reynolds numbers, the circulation varies monotonically with increasing area or increasing r. And as you increase r from say 1 to 1000, it reaches the Gaussian flatness of 3. And this is very similar to what happens for a velocity increment field. And this is the signature of intermittency, that the statistics are scale dependent. However, you increase your Reynolds number and then you do the same calculation again in this direction of this arrow. What you see is there's a plateau developing as you go from the smallest Reynolds number to the largest Reynolds number, where the circulation is, flatness is almost quasi-independent of the scale size. And this is a signature that the intermittency is weakening for this particular statistic. And in this inset, I'm showing you the circulation flatness. I'm focusing on the inertial range, which is defined by the 4/5 law. And I'm also showing you the corresponding flatness for the velocity increment field. I'm taking two different quantities here. I'm showing you both the longitudinal increment and the transverse increment. Both the flatness quantities for these velocity increments vary monotonically with r, and this is the signature of intermittency, whereas you see this plateau developing for circulation, which is absent for the velocity increment. So when you consider loops instead of say balls, what you're seeing is you are having less variation of the statistics on the scale size. So this is the signature of decreasing intermittency. So the circulation flatness shows a greater tendency to a plateau as you increase the Reynolds number. And this is nice because then you can define, say, the scaling features in a less complex way than you would for, say, the velocity increment field. In order to get the scaling characteristics, I would define circulation moments. Again, I'm going to consider a square loop with a edge length r, which is inside the inertial range. And I'm going to consider the pth order moments of the circulation. And I'm going to vary the loop size by varying edge length of this square. And what you see is these circulation moments, just like velocity increment moments, also show power loss. So we can get the scaling now. And you see that you can calculate these logarithmic local slopes to get these exponents very precisely. And what you see is now I'm going to show you the local slopes as a function of the moment order. But before I do that, I would like to point out that the Kolmogorov scaling, or the non-dimensional scaling for circulation, is 4p/3, which comes from the basic assumption that the velocity scales as the distance power 1/3. You see from the local slopes that the higher order local slopes fall below K41, so it's does not follow the self-similar estimate, but not by much. So what I'm going to do is I'm going to collect these plateaus. I'm going to collect lambda p, and I'm going to plot them as a function of p now. And when one does this, you will see something like this. So I'm plotting this scaling exponents. Here I'm considering the magnitude of the circulation. So I'm going to consider the pth order moment of the magnitude of the circulation. And let's say the scaling is lambda p here. And I'm going to plot this as a function of moment order. And I'm plotting it from -1 till 10. -1 is not included. At -1 it diverges. So I'm going to plot this whole thing, and what you see is you can explain this scaling behavior in a simple way using two functions. At the lower orders or the lower moments, you see that this scaling exponent is a linear function of p. It is still non-Kolmogorov. It is different than 4/3, but it is a linear function, which is nice. For the higher p, you see that the scaling exponents are almost linear functions of p, but the lower order scaling and the higher order scaling differ. So this is like a bifractal scaling that you see. And the scaling estimate that Migdal provided was exactly p. So what you see is there's a difference. It's a 10% difference here from Migdal's estimate in this data. And if you were to consider the area instead of the loop size r, you will see that the scaling is half according to Migdal's scaling, or you will see that the exponent is 0.55. So you can either use the edge length or the area to quantify the circulation. Here I've used the edge length r. And now I'm going to show you the average vorticity scaling. To do this, I'm going to again consider a square loop within the inertial range. This time I'm going to parameterize this loop with the area, which is r square. And what I'm doing is I'm going to consider the average vorticity, which is conditioned on these high circulation regions. So notice that when you consider large circulation magnitudes, so circulation divided by the viscosity is a circulation Reynolds number. So I'm considering regions where the circulation Reynolds number is large, and I'm showing you the average vorticity as a function of the area A of this loop. And what you see is in this inertial range, this is the intermediate range, you see that the scaling conforms to Migdal's scaling of 0.55. In fact, Migdal's scaling is 0.5. You see a small difference, as I mentioned already, but it's very close to the scaling proposed by Migdal, and it's different than the scaling proposed by Kolmogorov. So here, the next plot, I'm showing you the compensated plots, and what I'm doing is I'm going to multiply this ordinate with the a power 0.55, and if the scaling were right, then you will see a plateau. And here, and I'm showing you this on linear ordinates, so the test is a bit more stringent, and what you see is the Migdal scaling. There are some points in this flow where this Migdal scaling is obeyed, and this is also a function of Reynolds number. As you increase the Reynolds number or decrease it, this range of scaling range will change. So this inertial range scaling of the average vorticity, this comes about in these high circulation regions or high circulation magnitude regions, and this is very close to Migdal's prediction. So these large vorticity events reside in high circulation regions, and I've already shown you this PDF, and here I'm showing you the logarithm of the PDF of the circulation, and I'm showing you this as a function of the circulation Reynolds number, which is circulation divided by the viscosity. And you see that if you consider loops within the inertial range, they all collapse, and outside the inertial range, they diverge like this. So all the curves that collapse are within the inertial range, and when you consider such regions, you see that there is rich structure in this field. When you consider, this is the figure I showed you first up. So you consider the vorticity component normal to this plane, and you see this large structures, and this is conditioned on a high circulation region, which is shown here. And this is the basic essence of this work, that if you consider regions where you have large circulation, you see both structure and scaling, which you would not associate with isotropic turbulence. So to summarize my talk, circulation statistics depend essentially on the area of the loop and not on its aspect ratio, at least for planar loops. The situation is more complex for non-planar loops, as I showed you, and you need to consider normalized moments. Higher order scaling exponents are closely linear, so we are interested in higher order scaling because these are regions where high vorticity resides. And more importantly, loop averages seem to yield a simpler picture of turbulence than, say, this conventional ball averages in quantifying large vorticity structures. I would like to end my talk and take any questions if you have any.
Thank you. Any?
Yes.
Please.
Your comparisons with some analysis, some like some models, they are based on the analysis of data, right? So essentially, the data fit to certain dependence.
Yes.
How did you evaluate the goodness of your fit? Which statistical methods did you apply to evaluate the goodness of fit? Like, conduct an error analysis, and if so, what were the typical parameters of this goodness of fit, like statistical parameters? Because it's a very strong statement that you make, so it's very good to have it. These results to be statistically competent. So how do you ensure statistical confidence of your consideration?
So what I did to calculate the exponents was I calculated logarithmic local slopes and the regions where I saw on linear ordinates a plateau with 95% confidence interval. So I took that as the scaling exponent, as I showed. And there are...
But how sensitive were your results, for instance, if you will make your, interval, over your wave vectors, larger, smaller?
Yes, so if
because there is a hidden parameter.
Yes,
right?
exactly. So if you change, especially
you can always fit, and if your dynamic range is very small, you can always fit whatever -5 or actually choose any dependence, and you will be, you will find an appropriate range of vector values or
I agree.
Range of modes.
But the advantage with the high Reynolds number data set is as you'll have a large scaling range of almost a decade. So there it becomes less sensitive. So if you decrease the scaling, if you consider a smaller range or a wider range, the exponent doesn't change much. So we did do that error analysis where we changed the inertial range by a few % outside and inside for the highest Reynolds number.
Was it a parameter, quantitative parameter to evaluate it, like goodness of fit score or some other score?
So we calculate the root mean square error.
Root mean square error may not be it's a typical, it may be not very informative.
I agree. So that's what we did for this analysis. But
so you did root mean square.
Yes.
RMS, actually R2.
Yes.
You did R2.
Yes.
Yeah. So maybe some more.
I agree. Yeah. This is not as sophisticated as one would like eventually, but this is what we did, and it would be great to have a more robust system for evaluating these exponents because they're so critical in
because
many things.
Yes.
Yeah.
Okay.
I have a somewhat related question. Have you looked at how much uncertainty you get inherent in your DNS procedure? Because there is the sampling uncertainty, there is the discretization uncertainty, there is the energy budget uncertainty. Because if it is there, and if you are looking, for example, at a subtle deviation of the scaling from K41, it very well may be just because of the DNS itself. Have you looked at that?
Yes. So what we have done is we have evolved the DNS for a multiple integral time, eddy turnover times. So you can increase the sampling and decrease the sampling to see how the statistics change. We have done this analysis, and the exponents that I've shown you of the gamma varying as a per 0.55, that is not sensitive to this. So if you increase the data or if you decrease the data, we have made sure that it's not a function of that. But finite sampling is always an issue. Yes.
Yeah, so we may need to talk about that further, but...
Okay,
So
it's
I have a quick question here. How was your flatness related to the planarity that you compute from the Minkowski integrals?
So I'm showing you the flatness just as a signature of how the statistics are varying as a function of scale. So typically you would see what I'm showing you in the inset, where things are changing monotonically with scale. So what this does is the fourth order circulation moment is a non-trivial function of the second order moment. So what I would like to do is I would like to get scaling exponents that can be explained very simply with moment order, which you can't in the velocity field. So this is like a basic signature of intermittency. If the flatness is falling down steeply, that means the moments are a complex function of the moment order. That's why I show you the flatness.
All right, thank you.
Just a quick question.
Small question?
Yes, small comment. Here you measure circulation in its variance. And variance is not determined by large value of circulation. It's the tip.
Yeah.
So but you know very well what I'm going to say. If you instead measure everything in terms of the tails of distribution, like in terms of coefficient in the exponential, or nth root of nth moment, then non-universality will become less. Is it true?
So I've shown you that for the area rule, but the problem with normalizing with the high order moment is your statistics become more sensitive to sampling, because these high moments reside in the tails, and these are very sensitive to your the number of samples you have.
Yeah, just a question.
Okay.
I was the first. I was the first whom you pointed to us. Okay, so one question is, your characteristics in some way should be similar to characteristics of scalar dissipation of energy. And it's initially log normal and then it becomes exponential. So are these characteristics in some way similar, or they're completely different? Because you have these high dissipation regions, intermittency, and all other related stuff. So
yeah, I'm not sure whether it's log normal. I've not seen that behavior, but the basic, so you're talking about the moments of the, say, locally average dissipation, right?
Okay, yeah, it's a dissipation which is local, and then you average over a certain area, and you see log normal distributions and scaling, which is again would be corrected Kolmogorov scaling. It's a very important part of conventional theory of turbulence. I would check one against the other and see how they related or not related. Very important issue.
Okay, thanks.
Okay. Please discuss after this session. Thank you. Thanks to the speaker again.